Today we're starting Chapter 4, which focuses on the fundamentals of logic used in PLC programming. Understanding these concepts is critical because logic gates are the foundation of how PLCs make decisions. This slide introduces the concept of binary, which is the foundation of logic used in PLCs and digital systems. Binary means that something can exist in only one of two states, represented by 1 and 0. These states can take on many real-world meanings: on or off, open or closed, true or false, or high or low. For example, think of a light bulb. When it's on, that's represented as 1, and when it's off, it's represented as 0. In PLC programming, all decisions are built on this simple two-state system, which makes binary the language of control logic. For example, think about an automobile high beam light. It only comes on if both the main light switch and the high beam switch are closed. That's an AND condition. Both inputs must be true for the output to activate. Let's first take a look at the AND gate. An AND gate has 2 or more inputs and only one output. Notice that the output is 1 only in the very last case, when both inputs are 1. This is why the AND gate is often called the all conditions must be true gate. Think of it like a team project. If both team members don't complete their tasks, the project can't move forward. Both must say yes for the output to be yes. Logic gates are special digital circuits. That means their inputs and outputs can only be in two possible states, 0 or 1. Now, let's focus on a 2-input AND gate, which can have 4 different input combinations, and for each combination the output follows simple rules. If both inputs are 1, the output is 1. If either input is 0, the output is 0. Think of it like a light controlled by 2 switches in series. The light only turns on if both switches are flipped on. The AND logic gate operates similarly to control devices connected in series. The light will be on only when both switch A and switch B are closed. The next logic gate we will examine is the OR gate. An OR gate can have any number of inputs, but only one output. The OR gate output is 1 if 1 or more inputs are 1. This figure illustrates the 4 possible combinations of inputs for a 2-input OR gate. The basic rules that apply to an OR gate are: if 1 or more inputs are 1, the output is 1. If all inputs are 0, the output will be 0. This figure illustrates the OR function using both a hardwired circuit and its logic representation. In the hardwired example, switch A and switch B are wired in parallel to control a light. The light will turn on if either switch A, switch B, or both are closed, because current can flow through either path. The truth table confirms this. The output is 1 when one or both switches are closed, and only 0 when both are open. On the right, the logic symbol for the OR gate shows the same principle. The output goes high if at least one input is high. This makes the OR function useful for systems where multiple conditions can independently trigger the same action, such as alarms or safety indicators. The next logic function we will examine is the NOT function, which is also called an inverter. Unlike other logic gates, the NOT gate has only one input. Its job is to simply reverse or invert the input signal. If the input is 0, the output becomes 1. If the input is 1, the output becomes 0. In practical terms, the NOT gate is useful when we need the system to respond to the absence of a signal. For example, turning on a warning light when a sensor does not detect proper operating conditions. This figure explains the NOT function in more detail by focusing on its symbols. The small circle at the output of the gate indicates an inversion, meaning the signal is flipped. This is shown by placing a bar over the variable, which means not A. The result of the NOT operation is always the inverse of the input. If the input is 1, the output is 0. If the input is 0, the output is 1. Because it always produces the opposite state, the NOT gate is also called an inverter. This makes it essential in logic design when we need to respond to the absence of a signal rather than its presence. This figure shows how a NOT gate is combined with an AND gate to control a low-pressure indicator. When power is on and the pressure switch is open, meaning pressure is low, the switch signal is inverted by the NOT gate to a 1. With both inputs to the AND gate now equal to 1, the output is 1 and the low-pressure indicator turns on. When pressure is normal, the switch closes and sends a 1 into the NOT gate, which inverts it to 0. The AND gate now receives inputs of 1 and 0, producing an output of 0, so the indicator stays off. In short, the NOT gate reverses the pressure switch signal, so the warning light turns on only under low-pressure conditions and power is available. Another combination of basic gates that is useful is NAND function, which is simply an AND gate followed by a NOT gate. In other words, the NAND gate gives the opposite output of the AND gate. Looking at the truth table, when both inputs A and B are 1, the output becomes 0. In all other cases, when one or both inputs are 0, the output is 1. This makes the NAND gate a very powerful building block in digital logic, since it can be used to construct all other gates. For example, in control systems, a NAND gate could be used as a safety interlock, ensuring that if all conditions are simultaneously true, the output turns off rather than on. Similarly, we can use an OR gate followed by a NOT gate to form the NOR function. The NOR gate produces the exact opposite output of the OR gate. Looking at the truth table, the output is 1 only when both inputs, A and B, are 0. In every other case, when one or both inputs are 1, the output is 0. In practice, this means the NOR gate acts like a none of these detector. The output is high only if none of the inputs are active. For example, in a PLC safety circuit, a NOR gate could be used to ensure an output is energized only when no fault signals are present. The last function we will examine is the exclusive OR function, which is often referred to as the XOR function. The XOR outputs a 1 only when one input or the other is 1, but not both at the same time. This makes the XOR gate useful whenever we want to detect a difference between two signals. For example, it is often used for comparing binary numbers. If two bits are the same, the XOR output is 0. If they're different, the output is 1. In PLC applications, XOR logic could be applied to control a circuit that turns on a light only if exactly one switch is activated, preventing it from turning on when both switches are pressed simultaneously. Today we looked at the basic logic gates and how they form the foundation of digital control. In the next lecture, we'll move into Boolean algebra, the mathematical language behind these gates. Boolean algebra allows us to represent, combine, and simplify logic expressions, making PLC programs clearer and more efficient.